All right, as we get started today, I'm bringing us back to this reaction. Also, I'm handing out your possibly useful equations sheet for the final because there's a lot of equations on here, and I want you guys to be familiar with this tool, and that means I gotta make sure you have it. Gotta make sure you're looking at it. So this chemical reaction that we're watching, we discussed last class that it technically could be an acid-base reaction. But we also know a little bit better now that it can be what other type of reaction? What can we label this as? Once more with confidence. Oxidation reduction, aka redox. Yeah? What is being oxidized? What is being reduced? Let's answer this question first. What is the oxidizing agent? There's two ways to try and identify the oxidizing agent. You can find the species that is being oxidized, and it's the other compound that is the oxidizing agent. Or you can find the species that is being reduced, and that is the oxidizing agent. So really, you can kind of just guess any compound, check whether it's oxidized or reduced. If it is reduced, it is the oxidizing agent. If it is oxidized, the other thing is the oxidizing agent. So what do you guys notice? What's being oxidized? What's being reduced? What's the first thing that stands out to you in trying to solve this? It is unbalanced. Does it need to be balanced in order for us to solve oxidizing agents and reducing agents? Not really. So we can go through the balancing if you'd want to, but it's a little bit more complicated than we really need it to be for balancing. What do you look for? Which species do you want to identify first? Which one do you think is the easiest to identify as being oxidized or reduced? Copper is going through a change. Can I hear what you're saying a little bit more loudly? Copper goes from what oxidation state to what oxidation state? What is the oxidation state of copper at the start? 0. That's elemental copper. What is the oxidation state of copper in the products? -2? +2, because it is the cation of copper nitrate. You cannot figure out the which oxidation state you have of copper unless you know nitrate. This is one of the reasons you have to memorize your polyatomic ions. Although, actually, you get a little bit of a cheat on your final exam because some of those solubility rules are listed and some of your polyatomic ions are there. So, know your tools. They can be big helps to you. Copper goes from neutral to +2 oxidation state because we said that the oxidation state of a monoatomic ion is the charge of the ion. This is an ionic compound, true, but copper ion is monoatomic. From a 0 oxidation state to a +2 oxidation state, is copper gaining electrons or losing electrons? Losing. It's becoming more positive. So copper is oxidized or reduced? Oxidation is loss. Copper is oxidized. So is copper my oxidizing agent? Is copper the one that does the oxidizing? No, copper has oxidizing done on it. Copper is what reagent? The reducing agent. So what chemical here is the oxidizing agent? Nitric acid. Can we figure out what atom, not necessarily what species, but what atom is being reduced? Reduction is gain. So we know that nitric acid is being reduced. I want to know what atom in nitric acid is reduced. So we need to compare the oxidation states of all of the atoms in the starting materials and the oxidation state of all of the atoms in the products. That means I need to know their structures. I need to know how many bonds nitrogen has to other atoms and how many bonds the oxygens have and the hydrogen. So I have to draw out the structures for HNO3. I could look at nitrate, I could look at water and nitrogen dioxide. So HNO3 has this structure. Lone pairs, there are 2 on each oxygen except for the single bonded oxygen, which gets a third lone pair. There are formal charges. There's a negative charge on one oxygen and a positive charge on the nitrogen. Then we look at nitrate. Now there are 2 oxygen atoms with 3 lone pairs. That's 2 oxygens with a negative charge, 1 oxygen with a positive charge. I need to also consider what water might be. So I have to draw the Lewis structure for water. H2O, 2 lone pairs on oxygen. And then lastly, the Lewis structure for nitrogen dioxide. You guys will remember that nitrogen dioxide is an exception to our rule about octets. Sorry, blanked on that word for a minute. Nitrogen takes a radical electron here. It doesn't actually get to a full octet. It's neutral, but it has 2 formal charges. Let's start easy with hydrogen. What is the oxidation state of hydrogen in nitric acid? What is the oxidation state of hydrogen usually? +1. And that's because hydrogen is usually bonded to an atom that is more electronegative than it. Is hydrogen bonded to a more electronegative atom? Yes. So hydrogen takes a +1 oxidation state. Is that a formal charge? No, that's an oxidation state. That is, what if it was a formal charge? What if it lost that pair of electrons to the oxygen? What is the oxidation state of hydrogen in the products? +1. It's bonded in the exact same manner as it is in the starting material. Has hydrogen been oxidized, reduced, or neither? Neither. Hydrogen is going through a chemical change. It's now part of a new chemical, but it's not going through a redox change. Okay, what about the oxidation state for oxygen? What is the most common oxidation state for oxygen? -2. It is one of the most electronegative atoms, so it's rare that oxygen is bonded to anything less electronegative than it. Here, oxygen steals electrons from hydrogen and from nitrogen. That's a -2 oxidation state. What is the oxidation state of this oxygen? 2 bonds to nitrogen, it steals electrons in both bonds, -2 oxidation state. And the oxidation state of this oxygen, also -2, because it's stealing electrons from one bond, and we have to sum in the formal charge. So a -1 from the bond, a -1 from the formal charge, a -2 oxidation state. All of our oxygens in nitric acid have the same oxidation state. What about the oxidation states of nitrate? 2 of them should be very easy to solve. What's the oxidation state of this oxygen? Nothing's changed. It's the same oxidation state, -2. What about this oxygen? Nothing's changed. It's the same oxidation state, -2. This oxygen has gone through a change on the left. But it's still -2. It's now in the exact same bonding situation as this other oxygen. So far, oxygen has not gone through a redox. What about the oxygen in water? What is the oxidation state of oxygen and H2O? -2. Remember, the sum of all oxidation states must equal the charge of the structure. What's the charge of water? 0. Water is neutral. 1 plus, 1 plus, 2 minus, neutral. What is the charge of oxygen? I just realized I forgot a lone pair on my nitrogen dioxide. I forgot 2 lone pairs on my oxygens there. What's the oxidation state of O minus in nitrogen dioxide? -2. It looks exactly like all of these other oxygens. What is the oxidation state of the other oxygen in nitrogen dioxide? -2. Has oxygen gone through a redox change in this chemical reaction? No. So we've ruled out all of the other options, right? Can we prove that it is nitrogen that is being reduced? Reduction is a gain of electrons, so I should expect that the oxidation state becomes more negative. What is the oxidation state of nitrogen in the starting material? No, good try. +5?
No.
Yes.
Yes.
Oh, yes,
Nitrogen loses electron to O, loses electron to O, loses electrons twice to O. That's a +4 oxidation state just from the bonds. And then you have to sum in the formal charge. So +4 oxidation state from each bond, +1 from the formal charge. That's a +5 oxidation state. What is the oxidation state of nitrogen in nitrate? It's still +5. So nitrate is not a redox product. Nothing has been oxidized or reduced in nitrate relative to nitric acid. But what about nitrogen dioxide? +1, +2, +3, +4. Have we gone more negative? Really? We didn't go negative at all, though. It's still positive. We went from a +5 oxidation state to a +4 oxidation state. That is what I call more negative. Despite the fact that it's still a positive number, we're getting closer to a negative number. Nitrogen has gained electrons, which is why its oxidation state is now a smaller positive number, a more negative number. Okay. That's the guess and check process that you have to go through to be able to determine which atom specifically is being oxidized. But eventually, you get to a point where you say, well, hydrogen stays in normal environments. Oxygen stays in its normal environments. The nitrogen seems to be changing its bonding environment. So I'm going to investigate nitrogen first because I suspect that one is being reduced. And if nitrogen doesn't seem to be reduced, then I'll try to find another culprit. Let's go through these last couple of oxidizing and reducing questions that we had on our sheet together. First, we're looking at iron reacting with copper to sulfate to form iron 2 sulfate and copper. You'll notice underneath it I've placed element reduced, reducing agent, and element oxidized and oxidizing agent. So I want you to be able to identify all of those different ways of looking at it. Reduction is what of electrons? Reduction is gain or loss? Reduction is gain of electrons. Has anything happened to sulfate in this chemical reaction? It stays an ion. So I'm not going to investigate oxygen or sulfate for its oxidation state. What element has gained electrons? Iron to iron 2 plus or copper 2 plus to copper? What element has gained electrons? Copper 2 plus to copper neutral. That is our element reduced. So the reducing agent iron. Should I put Fe or should I put Fe2 plus? Which one is giving the electrons away? If this is my element reduced, what is doing the reducing? Fe or Fe2 plus? Fe is doing the reducing. Fe2 plus is what forms. The element oxidized. Fe. Oxidizing agent. You want to say copper or copper 2 plus? What species is taking electrons? Copper or copper 2 plus? Copper 2 plus takes electrons to become copper. Our oxidizing agent is copper 2 plus. Clear as mud? Our last reaction is a combustion reaction. This is what happens when you burn natural gas. It's a very good chance that your house is heated by a natural gas combustion furnace. So the question is, what is being oxidized? What is being reduced? In a combustion reaction, you can actually see the definition of oxidation a little bit more clearly. Literally, what atom is getting oxidized? Carbon gets all these oxygens. Now, to be fair, hydrogen is also bonding to oxygen in the products, but hydrogen started at a +1 oxidation state because it's losing its electrons to carbon, and hydrogen ends in a +1 oxidation state. But carbon starts with what oxidation state? -4. It steals electrons from all 4 hydrogens, and carbon ends with what oxidation state? +4. It loses electrons to 4 bonds to oxygens. More positive or more negative? More more positive? Oxidation or reduction? Oxidation. Our oxidized element here is carbon, not necessarily CH4. The hydrogens are not being oxidized. Their oxidation state stays the same. So our oxidizing agent surely it's oxygen. What is the oxidation state of oxygen in the starting materials? Raise of hands. Jordan?
It's zero.
Zero. This is elemental oxygen. It's not bonded to anything more positive or more negative, more electronegative or less electronegative. No charge. Zero oxidation state. And the oxidation state of oxygen in the products. Here, each oxygen bonds to carbon twice, stealing electrons. And here, the oxygen bonds to two hydrogens, stealing electrons. 2 minus. So the atom that has been reduced, O2, the reducing agent, carbon, and to be fair, we could actually say here CH4. Methane is the reducing agent, but it is carbon specifically that's being oxidized in there. Just to be clear, carbon is oxidized, not hydrogen, but the source of carbon is methane. So we can say methane is doing the reducing, and by doing that, it's the carbon specifically. Okay. That is the end of Module 15, I gotta say. We took way too long going through that module. Module 14, sorry. So we're moving into Module 15. We're gonna wrap up Unit 6 on reactions today. And then if we have the time for it, we're gonna move into Unit 7 and start talking about gases. I have uploaded a few new assignments, or not assignments, a few new documents onto Canvas for all of you. If you look at the Unit 6 module, I've uploaded a Unit 6 Learning Objectives document. So this goes through and it talks about what are all of those skills that ideally you get out of this unit. I've also uploaded the Unit 7 Learning Objectives document as well, so you can kind of look ahead and see which modules inside of Unit 7 are a little bit heavier than the other modules. Which ones have less bullet points, which ones have more bullet points. Sorry, I don't know why it's uploading like that. So that's a good resource for you when you're preparing your cheat sheet, or if you're going through the Real Chem homework, you can kind of look at this and say, how does the question I'm looking at apply to the learning objectives that we had for this section? So in Module 15, we're talking about stoichiometry. Does anybody remember from their readings what stoichiometry means? What is the definition of stoichiometry? A lot of people refer to this as stoic. When they're doing stoichiometry, they're talking about the stoic of the reaction. Stoichiometry is a really unnecessarily big word for something that we've basically already talked about. The mole ratio of chemicals in a reaction. That's stoic. And we've already looked at mole ratios. We've said that, for instance, in water, there are 2 moles of hydrogen per 1 mole of H2O. All we're saying now is that 2 moles of oxygen produce 1 mole of CO2. These are mole to mole ratios. 1 mole CO2 produced by 2 moles of O2. And again, we can write these mole ratios in any direction that we want to. We have to keep the coefficients from the balanced chemical equation, but we can put moles of whatever on top and moles of whatever on bottom. What's the benefit of being able to write our conversion factor right side up or upside down? You can cancel out the units that you want to. If you have information about oxygen, then you want to cancel moles of oxygen and you put it on the bottom. If you have information about carbon dioxide, then you want to put carbon dioxide on the bottom so that it can cancel out. This is exactly the same thing we've been looking at with dimensional analysis all semester long. I can say 1 meter is 1 billion nanometers, or I can say 1 billion nanometers is 1 meter. I can flip my conversion factors upside down whenever I want to. So it is the coefficients from the balanced chemical equation that we need here. I want to remind you guys of our roadmap. We had this map in an earlier handout where we looked at moles of A to moles of B. And what did we use as our conversion factor here? The mole ratio, which now we're just calling the stoichiometry. Do you guys remember some of the other pieces of this roadmap? What else can we convert things to and from? Mass. If I have moles of something, I can determine the mass of that thing. Particles. What else? The molarity. Actually, I changed my mind about how I said this, and instead we can find the volume. I put liters, but I should have put volume. The reason I changed that is because the conversion factor is molarity, moles per liter, which means the two things I can convert between is volume and moles. What else? Wasn't there one other? No, that was it. Let's talk about the conversion factors that are needed. What conversion factor gets me from moles to particles? Avogadro's number. From moles to mass? Molar mass. And like we just said, moles to volume? Molarity, moles per liter, big M. I want you to notice that all of these conversion factors have 2 units. That's the defining piece of a conversion factor. Things per mole, grams per mole, moles per liter, moles per moles. If you have something that has 2 units, that is a conversion factor. All right. In chemical reactions, we can say that I need a specific number of moles to react with a specific number of moles of another reactant. But that doesn't mean that I have those ratios. So, when the actual amounts differ from our balanced coefficients? I can say that I need 1 mole of of methane to react with 2 moles of oxygen, but that doesn't mean I have 1 mole of methane and 2 moles of oxygen. What if I have 1 mole of methane and 10 moles of oxygen? Will all of the oxygen react? No. The oxygen will react 2 moles, and then there will be 8 moles of oxygen that don't react. This is what we call an excess reagent. There is more of it than meets the ratio of the stoichiometry. And so the excess reactant will have some unreacted. How might you define a limiting reagent? Completely consumed. And maybe I should have actually rephrased excess reagent. Excess reagent is left partially unreacted. It's not to say that it doesn't react at all. Some is left unreacted. It's left partially unreacted. There's leftover of the excess. So why would we call it limiting? What is it limiting? Yeah, it limits how many moles can react. It limits how many moles of product can be made. So, an analogy, I have 10 pieces of bread, and I need 2 pieces of bread to make 1 sandwich. How many sandwiches can I make? 5 sandwiches. What is this? The stoichiometry, the mole-to-mole ratio. And I have 8 pieces of turkey, and I need 1 piece of turkey for every sandwich. How many sandwiches can I make? With the turkey. With the turkey, I can make 8 sandwiches. From a logistics point, I can only make 5 sandwiches. I have enough turkey to make 8 sandwiches, but I will never make 8 sandwiches. That is wishful thinking. Somebody is going to get a double open-faced sandwich, no bread on it. Exactly. And then I'd actually have excess bread. Yeah? So Ryan's suggestion was, what if I put 2 pieces of turkey in a sandwich? Now how many sandwiches can I make? 4. I just went from turkey being the excess reagent, and now turkey is the limiting reagent. The easiest way to determine whether something is the excess or the limiting reagent is to pick a common product and look at how much both of those compounds can make of that product. The one that makes the smallest amount of product is the limiting reagent. see which reactant makes a smaller amount. Let's do an example with the Haber-Bosch process. You guys remember the usefulness of the Haber-Bosch process? What it does in real life? It makes the ammonia that we can put into fertilizers so that plants have a source of nitrogen. Is this balanced? Anybody want to raise their hands and offer coefficients that would balance it? Ryan? That was quick. You don't need to be that quick. You just need to have the skills to do it. What would you have done if I gave you more time? Account for all the atoms on the left, account for all the atoms on the right, pick somewhere to start, add coefficients, see how that changes things. But now I've got 2 nitrogens, 6 hydrogens, 6 hydrogens. All right. When 60 moles of H2 react with 40 moles of N2, what is limiting? So we'll take both of our reactants, we'll convert them into a common product, and we'll see which one makes less of that common product. 60 moles of H2. I need to put moles of H2 on the bottom. And I'm going to convert into moles of NH3. There's only one product, so picking a common product is pretty easy. What are my coefficients here? Two over 3. 2 moles of NH3 require 3 moles of H2O. 60 times 2, 120, divided by 3, I can make 40 moles of ammonia. Does that seem valid? For every 3 moles of H2, I only make 2 moles of NH3, so I make a smaller amount of NH3. Now, 40 moles of N2, I need to cancel moles of N2, so I'll put it on the bottom. What should I put on the top? Moles of ammonia. I'm trying to get to a similar perspective. Just like in the analogy, we were always going to sandwiches so that we could compare in the same dimension. We're going again to moles of ammonia. And what coefficients do I put here? Somebody else? One more time. 2 on the top, 1 on the bottom. 2 moles of NH3 can be produced from 1 mole of N2. It's clear that these coefficients are not coming out of nowhere, right? They're coming from the balanced chemical equation. 40 times 2, I can make 80 moles of ammonia. What is my limiting reagent? H2 is limiting the reagent here. H2 is limiting the reaction. Do you know there is another way that you can do this? Rather than looking at a common product, you can actually ask, if I have 60 moles of H2, how many moles of N2 would then be required to react here? So you can kind of see what would be needed in order to consume all of the H2. We could say 60 moles of H2, converting from moles of H2 into moles of N2. What are my coefficients here? One mole of N2 requires 3 moles of H2. 60 divided by 3, 20 moles. This conversion is saying I only need 20 moles of N2 to consume 60 moles of H2. If I have 60 moles of H2, 20 moles of N2 will react with it completely. Do I have 20 moles of N2? Yeah, and more. So N2 is my excess reagent. I've proven this 2 different ways. N2 is excess reagent because it is capable of making more product, but it will run out of H2 before it can get there. N2 is my excess reagent because I have more N2 than I need to completely react with the H2. So there's a bit of a logic puzzle you have to solve there. We ran into the instance where converting H2 into N2 told us we need less N2 than what we have. This could have been the other way around. We could have converted N2 into H2. If we had done 40 moles of N2, and we divide 1 mole of N2 by 3 moles of H2, we can see here that I would need 120 moles of H2. Do I have 120 moles of H2? So I will never be able to consume all of that N2. H2 is the limiting reagent. I like to really make sure I'm doing it right, and I like to take both of my reactants to a single product. That way I can feel confident that I'm always looking at a common denominator. But this route, it's technically less work, right? Because all I had to do was one conversion to figure out that N2 was going to be in excess. Going to the common product, I always have to do 2 conversions. But it's just a little bit less logic puzzly to have to solve. Okay, we're going to be doing some of this like excess limiting, but I want to talk about types of reactions that we go through as well. Or, analysis reactions that we use. And actually, before I get there, it's important to talk about percent yield. Percent yield is something experimental. Percent yield is when you, in theory, can make a certain amount of product based on the reagents that you have present, but in practice, don't get that exact amount. Percent yield is calculated as the experimental yield or the actual yield divided by the theoretical yield. And then, of course, as with every percent, we multiply by 100. The theoretical yield is just that. It's all theory. It's doing stoichiometry. The experimental yield or the actual yield is something that you have to measure hands-on in a lab. You're comparing reality against theory. So actually, let's do a practice problem looking at limiting and excess reagents and calculating the theoretical yield. We're going to say that 1.31 grams of calcium carbonate decomposes into calcium oxide. Whoops, I didn't mean to give you the chemical formula. And carbon dioxide. What is the percent yield? If 0.53 grams of carbon dioxide is captured. What's the challenging part about this? You have to write out the chemical equation as well. Chemical equation is given to you in words. You need to translate it into chemical formulas. Here you go, Sarah. Just this one for now. Let's talk through it. I'd like different people to engage in the different parts. Calcium carbonate. What's the chemical formula? Raise of hands. Think.
Is it CaCO3?
Good.
Calcium has a +2 charge and carbonate has a -2 charge, so it's already balanced.
Perfect. They balance 1 to 1, calcium 2 plus, and CO3 2 minus. Decomposes means there's nothing else that's reacting here. It just turns into, now can anyone give me the chemical formula for calcium oxide? Raise of hands. I'm going to force you quieter ones to talk. You know something that's in that chemical formula. All right, Jordan, let's hear it. Calcium oxide.
Is it just
CaO. Calcium 2 plus, oxide 2 minus. All right, now this one's a softball. Carbon dioxide. Come Come on. CO2. Thank you, Cole. Is it balanced? It is balanced. 1 calcium, 1 carbon, 3 oxygens. Okay, I didn't realize this actually doesn't have a limiting or excess reagent. Why not? No, there's only 1 reagent. There's only 1 reactant, so there can't be a reactant that limits the yield or excesses the yield. There's just 1 thing. But we are saying that 1.31 grams of calcium carbonate, it can be converted into either calcium oxide or carbon dioxide, but I only know the mass of carbon dioxide that was captured, so I want to make sure I convert into carbon dioxide. What should my first conversion be? What goes on the bottom? Yeah, I need to use the molar mass. So what unit of molar mass should go on the bottom? Grams or moles? Grams. Grams of calcium carbonate into moles of calcium carbonate. Here we have to do a little bit of calculator exercise. 16 times 3, 48, plus 12, 60, plus 40. We're looking at about a molar mass of 100. Calcium's 40. So 100 on top or 100 on bottom? 100 grams per how many moles? That's what you get from the periodic table. It's always mass per 1 mole. Do I care about moles of calcium carbonate? No, so I'm going to convert. Moles of calcium carbonate goes on the bottom. What should go on the top? Moles of CO2. Where do I get values to fill in this mole to mole ratio? Good, the balanced chemical equation. I take the coefficients. What's the coefficient on CO2? What's the coefficient on CaCO3? 1-to-1 conversion. Do I care about moles of CO2? No, I want what? I want grams of CO2, so I want to cancel moles of CO2. What is that? What is that? Molar mass. Carbon weighs 12, 2 oxygens is 32, 32 and 12 is 44. 44 should go on the bottom again? No, 44 grams per mole. Okay, question, do you think 1.31 grams of calcium carbonate will weigh more as carbon dioxide or will weigh less as carbon dioxide? Carbon dioxide weighs less per mole than calcium carbonate. So if I'm making the same number of moles, this final theoretical mass should be lower. Cancel out all my units. 44 times 1.31 divided by 100. Somebody want to give me what they get? 0.57 what? 64. Let's keep it all out for now, and we'll round our sig figs at the end. The theory is telling me that I can make 0.5764 grams. Did I make 0.5764 grams? I did not. When I do my percent yield calculation, which of these numbers should go on top? 0.57 or 0.53? Which is the actual yield? What was actually weighed in the experiment? 0.53. And how much should I have gotten in theory? 0.5764. Times 100. What do we get? So here we'll round it to 2 sig figs. So 91. 92% yield. We actually saved ourselves a step by having a decomposition reaction. If this was actually a chemical reaction, 2 reactants, this is a chemical reaction. If we had 2 reactants, we would have had to solve for the theoretical yield twice. We would have had to determine which is the limiting reagent, which is the excess reagent, because that would tell us what the actual theoretical yield was. We got off easy because we only had 1 reactant, 1 theoretical yield. Okay, on the back side of last class's worksheet, we have a bunch of reactions. In these reactions, we're utilizing some analytical techniques. The first of these techniques is called titration. Titration involves acid-base reactions. Specifically, it's most often looking for neutralization, where every mole of acid reacts with every mole of base, and no acid and no base is left over. We're looking for that mole ratio in the acid-base reaction. One of the most important parts of titration is the equivalence point. This is where the moles of acid equal the moles of base. No, you know what? That's confusing. It's the mole ratio. I'm going to say this. Moles of acid, moles of base. Well, I'm even just saying A and B. I mean to say acid and base. Moles of acid, moles of base equals the stoic mole ratio. We want their balanced chemical coefficients to be the same as what we see in here. We want them to completely react as they would in a balanced neutralization reaction. That's what we find at the equivalence point. Every mole of acid reacts with every mole of base. Everything is consumed. The other analytical technique that we use is gravimetric analysis. What do you hear in gravimetric analysis? Gravity. Rather than titration, which uses chemical indicators that change color, which tell us when all of the acid has been consumed or when all of the base has been consumed, gravimetric analysis has to isolate the products and weigh them. That's similar to what we did there, where we isolated some carbon dioxide, we got its mass. That was a gravimetric analysis of the reaction. One of the most common things here is to filter precipitates and then weigh them. If we have a precipitation reaction, we just isolate the precipitate and get its mass. Now that we know the mass of the precipitate, we can do theoretical yield calculations on how much I should have had. A subtype of gravimetric analysis is combustion analysis. Combustion analysis isolates the carbon dioxide and the water. We have materials that can separate these specifically. We talked about MOFs earlier in the semester, metal organic frameworks, which just won the Nobel Prize in chemistry. And MOFs are good at selectively isolating different compounds like this. And then we can take the mass of the carbon dioxide, the mass of the water, and we can determine information about the starting materials that way. All right. I do want you guys to have a chance to have a break. So why don't you take this opportunity to get up and move around and get your blood flowing. And when you come back in, I'd encourage you to work in groups. I might even nudge you guys to work in groups and solve some of these equations on the backhand side. You'll have to first write out the chemical equation, balance it, and then answer the questions that it asks you. I'll be coming around to answer questions. Let's spend about 15 to 20 minutes on this backside. So when you get stuck, just move to the next one, see what you can do about the next one. All right? Peter, did I give you one of these? No. I got one left. This one?
Is that your last one?
No.
Okay.
This is your final
What, like,
so I want you to have it, especially for what we're going into next.
I was
All right, if you haven't already, now's the right time to start working on solving those problems. Write out the chemical equations, balance them, start answering the questions it's asking you.
Oh, that's
You know what? I'm changing my mind. I'm gonna break you into groups to solve one of these 4 problems. And then together, your group will help me interpret it to the rest of the class. Okay, so you're gonna have to probably do a little bit of moving around. We'll have the 5 of you, when Peter comes back, work on problem number 4. And the, how many are, there's 6 of you. You guys will work on problem number 3. In the back, you 4 will do problem number 2. And you'll also take Jackson when he comes back, problem number 2. And up front, when Saint gets back, the 4 of you will do problem number 1. So just work on your 1 equation. And then together, we'll go through all of them. So Sarah, you'll have to, you can scoot your chair. They don't, the class that did this before, they don't care about organization.
Oh wait, oh.
Mm-hmm. I think my hardest problems, my strongest soldiers. Good luck. How you thought about it. When you teach others, they praise it. Oh, shoot. That's NO3 minus. Well, it tells you the products. It doesn't tell you the products exactly. Sorry. Wait. Okay, it doesn't tell you directly. It says iron 3 oxide reacts with an excess amount of carbon monoxide. Those are your reactants. And then A, it says iron metal is formed. And B, it says carbon dioxide is formed. Those are your two products.
Oh, so there's two.
And iron metals.
This iron then? Oh, okay.
Yep.
So Fe.
Yeah. CO2. So that was a bit confusing. My bad. You had to go through part A and part B. The products.
All good. Okay, so Fe2O3 plus CO gives
I've got a nice little square going.
Carbon monoxide is just CO, right?
The oxygen but it's reacting with it.
So I need to balance the equation.
You don't have an equation yet.
Okay. Oh, I thought it had
This plus this equals. These are the two reactions.
Oh, I don't need all this is reaction oxygen.
This reacts with carbon monoxide. First, I mean, this certainly would be balanced, right? So we're saying nuclear fission, iron decomposes into carbon. Okay. And then one of your products is an A, iron metal. So the other product is a B. Good. Yep. It's silver. I wonder if you could just twist so that maybe it's a little bit more in the. There you go. Did you guys figure out the chemical equation? Yeah? You've got decomposition, which is similar to what we just did. So one starting material, two different products. Good. By the way, this is the chemical that you use in like an airplane when you have to pull down and put oxygen in. This is how they produce oxygen.
Sorry, I mean interrupted
You know, here you go.
So you've
No,
got
it's okay, you
got
can
the
ask.
chemical
I
equation.
did,
Now
so
you're
we
ready
have
for your
Fe2O3.
stoichiometry.
Is it 1 mole of Fe or
This is a bit of a reverse one, right? I want to
like
breathe in
coefficients
yeah,
of it.
oxygen.
We haven't put
How much
coefficients
starting
yet.
material will I
Yeah, so
need
you're just
for that?
writing out the chemical equation.
So if you're thinking about your roadmap,
So you have
moles to
iron
moles,
3,
grams to grams,
iron, oxygen,
where do you fall on the roadmap?
balancing out like
What
in
conversions
yours
do you
two,
need to do?
and this one's 3. And then it reacts with carbon monoxide, and then you have to go through a balance equation.
Chemical
And
formula
then that's why I was
here.
gonna ask you, did you get a 5 too?
Hydrogen
You
can't
got a
take
5
out
too?
a plus
Then
charge.
did you do, what did you
Only
get
take
the
out
5 by the oxygen? Is that what you got to do?
plus
Yeah,
charge.
oh,
Which
just
is
like
like
add
the
up amount of oxygen. Yeah.
balance.
Fine. Would you like to go to 2?
Well, that would give me a
So,
plus one overall
balance.
to balance phosphate.
I did two, yeah, so
Three H pluses.
at the beginning, we have 2 iron
Chemical
on the
formula.
left, 1 iron on the right. 4 oxygens
Chemical
on the
formula is
left,
this. Subscript.
2 on the right, 1 hydrogen on the left, and 1 on the right. So
You
all of
changed
the
from
oxygen
phosphate
last
to
just because
sulfate.
it became really messy, oxygen, hydrogen. So I started by balancing
Would you like
iron.
to visit this
I put in coefficient of 2 in front of it. On the right side. On the right side, yeah. So that gives me 2 iron on the right, and then the oxygen and the carbon stay the same. And then I move on to the
Start thinking about what conversions you are going to need to do. What information do you have? What information do you want? Think about where you are on a roadmap and where you want to go in that roadmap. Okay, well,
but then
sorry for moving your stuff.
so you have to multiply it by a fraction of 5 over 2, right? Yeah, that's what I did. But
We weren't super sure.
Cation.
I was like, well, I need a.
So it should be AG by.
Okay, so we have.
So this is a limiting and excess equation.
Oh, that's what this is asking?
Yeah.
So
So
which
yours,
one's the X
you're essentially figuring out which one is the next. So, what is your chemical equation?
So we're trying to get to the volume.
Good. Yep.
To the product, not products, reactants.
Yeah. So you can see that the iodine will fall out of solution, the silver will fall out of solution, but one of them will run out of the other ions to actually precipitate with.
How would you even know if it didn't tell you how much iron?
So how much potassium iodide do you have?
Oh, wait, you're confused on the products?
Yeah, how do you know the product?
0.65
Yeah,
grams.
is that so?
How much
Question
silver
one, like,
iodide
question
in that?
tells you the reactants
How much
of
silver
iron
nitrate do you
oxide.
have? How much
And then
silver
he said that
iodide
he
in that?
set up the problem.
And then one of them is going to be able to produce a smaller amount of silver iodide.
How much
That will
iron,
limit
how much
the
iron,
reaction
metal, so that's just like atomic or
Yep.
elemental iron, so Fe is one of your products.
Okay.
And then carbon dioxide, so
Imagine if I had to do all of them.
is your product.
This was much
Would
better.
be dead. So it's just like tricky words. If that makes sense. Yeah. If you balance it, that's what yeah. So we have the like volume and molecule of for example, okay, so we have calcium hydroxide because that's the 0.27 mole over 4 milliliters. And so then we need to
Don't forget to try and use your roadmap. Find information you have to land you on the roadmap, and then figure out what conversions to do. So if you want this number to be 5, what number can you multiply by 2 to give you 5? We're going to change the coefficient 2. It doesn't matter if it's 2, 10, 12, 100, 0. We're going to set a new coefficient. 5 over 2 times 2 gives me 5. And then multiply the whole thing by 2. Yeah, absolutely. Oh, no, that's right.
That's okay.
2 times 1, 2 times 2, 2 times 2, 2 times 5 over 2.
Okay.
Just distribute it.
Thank you.
Jackson, while you were out, I wrote this all with these guys solving problem number 1 on last Monday's worksheet. They got the chemical formula, so we're just trying to do some stoichiometry calculations. That's okay.
Yeah, but when for my carbon, so I'm going back to my adding everything. Okay. No, because there would be 5 carbons. No, it's saying 5. So there's 5 carbons there, and there's 5 oxygens.
When you balance chemical equation, or in your mole molarity, are you using the coefficient
What I want to do is direct you to the board. What information do we have? Typically, information with one unit is a good place to start. What information do we have in the body that has one unit? We want 2 kilograms of oxygen. So that's where we're going to start on our road. We're going to start with kilograms of oxygen. Which means even our logical goes convert into moles.
We've gotten as far as.
Then I can convert into moles. And then from there, grams of
CO2 from.
So you had the right idea. You wanted this. We actually want to target towards that direction. From that.
And we're trying to like down, and that's where the coefficient is. And then you go, it's times.
Yep. Yep. You gotta use,
And then you go.
I mean, eventually that cycle will kind of die down and you figure out what your coefficients need. So that there is coefficients.
Grams per mole of the
And same got there eventually.
which
You wanna,
I did. I'm lost now. So I went through.
it didn't balance?
I tried to balance it, so basically I was telling them that I put 5/2 to get a 5 on the right hand side, got to a 5 on the left hand side. And then when I go through and I'm doing like my accounting, I have 2 irons and I have 2 oxygens. Now I have 5 carbons. Yeah, 5 carbons. And so now I have to go to the right hand side and I have to change the coefficient of this 2 to a 5/2.
So I think it converted to grams.
Which changes my maybe not.
Yeah, because that's cool. Well,
So we're gonna stuck just on the balanced coefficients.
Yeah.
Laura, do you feel like you have one?
I think I do.
You know what? I never saw it. Coefficient for iron makes sense. Yep. Yeah. So if you've got an automaton of this, you get an automaton of that. It looks balanced. Yeah. Yeah. So I think take Laura's coefficients. Laura, maybe you can walk them through just that process again. And that intuition you had of I've got an even number here, so I'm gonna have to get an even number here. Walk me through that.
Okay. So I use the O2 I have as a little sheet for me. So I'm like, as long as I can get this to a different number on this side for oxygen, then I can change this to whatever I need to that.
Yep.
So, like, well, if I'm free here.
So in the bottom, you're saying this is limited. Yeah. And then you're saying silver nitrate is excess. Good. So we want to know how much of the silver will be left over.
CO2, so the coefficient balance out the number that you have on the right hand side.
Okay, so your idea is this is actually how much will precipitate.
That's really smart.
The answer you get here is how much of the silver will actually precipitate, and then you could subtract it. The difference would be how much is left.
But,
Although actually, now that I say that, if we want to say, yeah, you know what, it's good. It's good. It's good. You could actually say how many grams of light, or how many moles of actual. No, this is right. Sorry. Go ahead. Yep. So you figured out the precipitous.
yeah.
And I'm not sure what these are. Yeah. Oh, okay. Yeah, not a bad idea.
really big.
The question though was,
I don't know if I
which ion will stay in solution? Will iodide stay in solution, or will silver stay in solution? Silver and iodide are precipitated. What is the chemical formula for
Wait, but you still have
silver iodide. Which of these ions, silver or iodide, will stay in solution? Which of these is in excess? Mhm. Yeah, I agree from what your work is saying, although it seems. Oh yeah, I'm sorry. This is the limiting reagent, right? This produces the least amount of precipitate, which means this will be in excess. So we actually need to figure out how much iodide will be left over. So I think we're just multiplying by one.
Oh.
Problem. See, you want to say this is how much iodine is present and could precipitate, but this is how much will actually precipitate. What's the difference between those two? Yeah. Yeah, that's how much would be left over. Mm-hmm. They're thinking a little bit further, and they're figuring out the math. But it wasn't clear in the question whether you're going for mass or moles. So either one is okay. Once you have the number of moles, you could multiply by its molar mass. Mass of one. Mm-hmm. Yeah. This is how many moles you'll be able to make of this. In terms of mass. I think so. So what I was just telling Peter is we could have actually said if this is the limiting, this is the excess, what's the difference between these two? 0.0001 moles, right? This could have made 0.0039 moles of product, but it won't. It will only make this many, which means 0.0001 moles will be left over. So if you took 0.0001 multiplied it by this, yes, so I guess that number to me would not be exactly that. That might just be. You're doing calculations with 0.0039. That's the excess amount, which means that's not what's actually reacting. This is the limiting amount. That's actually what's reacting.
Don't know if that gives us how many milliliters it requires to reach the
That's this one's molar mass. That's how much will actually precipitate out.
Yeah. Wait. Oh, yeah. Oh, that's what we got.
Yeah.
Yeah.
Silver nitrate, that's doing a lot. That's what I'm like.
No, silver nitrate is limiting. Silver.
Oh, yeah.
Silver nitrate is limiting. Potassium iodide is excess and remains in solution. Yep. I think you multiplied this number times that and then added a number extra. All right, what do you guys find? Oh, it seems wrong. Seems really far. It seems like a lot, right? One thing that I maybe should have pointed out earlier is when we start these conversions, it's nice to start with a piece of information that has one unit. So in here we've got 20 milliliters. That's 1 unit. 0.2 molar. Is that 1 unit? It's actually 2 units in a trench coat. Moles per liter, which means molarity is a conversion factor. Okay, so we'll use it as a conversion factor. We're not going to start with it. You can, and the conversions will work out at its easiest if you start with something that has one piece of unit. 1 molar, is that 1 unit or 2 units? Yeah. So we're going to start with 20 mils, and then we're going to do our conversion. Looking at the roadmap, we're going to convert from volume into moles using molar, using the concentration. Oh, yes. What'd you get? 6.99. I don't know why you got it. Sure, what'd you get? Good. And 152 grams of carbon dioxide. Yeah, so it's actually of the ions of silver iodide, which would still be in solution. Which one is not in solution? Yeah. They were getting like 0.0001, but that's 0.00009 is very close. Rounding, just a rounding thing. But yes, that's exactly right. Good job. Always. So you could have said that as well, which will remain in solution, but that's like, that's about it. That's fair. Okay, shall we go through these? All right. Question number 1. My group up here. What is the chemical formulas? We can talk about the balancing after, but give me the chemical formulas for your reaction.
Fe2O3 plus CO reacts to form Fe and CO2.
All right, a bit of a confusing piece in what I gave here. It says iron 2 oxide iron 3 oxide reacts with carbon monoxide in excess. And then in A, I say that iron metal is formed, and in B, I say that carbon dioxide is formed. So I didn't do a great job of clarifying what the true chemical equation was, all in the wording of 1. Part A says, if 10 grams of iron 3 oxide reacts, oh, we need to balance, right? So you guys found that balancing was a bit challenging. We can start by trying to balance the iron. That should seem pretty easy. Coefficient 2 in front of elemental iron. Carbon is already balanced, so now we just aim to balance oxygen. I've got 4 oxygens on the left, 2 oxygens on the right. Where'd you go from here?
I have no clue how to explain it.
What were the vibes?
I knew I needed more of the CO on the left, so first I did a 2.
Yeah?
See what that would do.
And then, of course, you're going to have to correct that with the 2 over here. So now you've got 3 and 2 is 5, and you've got 4 on the right. Yeah? So if I've got 5 here, 4 on the right, I need to find a way to try and get my oxygens to balance. If I can get even numbers here really easily. This is able to give me even and odd numbers. So I'm going to try to find coefficients on these 2 chemicals that will add together to give me an even number. 5 and 4 was not it, but 5 and 4 was closer than 4 and 2. So if I just keep going up, I might be able to find another answer. If I change this from 2 to 3, I can get 6 oxygens on the right. How can I get 6 oxygens on the left? Here's 3. This is a source of an odd number of oxygens. So coefficient 3 here. 3 and 3 is 6. 3 and 2 is 6. The vibes are weird. This is a bit of a guess and check situation where you keep trying to get to a closer combination, and then you ultimately come down to the fact that this can give you even and odd numbers of oxygens, where this will only give you even. So you can manipulate this side a little bit better to make it match with an even number on the right. All right, there's our chemical equation. Yes?
I was going to say, Laura said too that she found a common multiple between 2 and 3. So the subscript of 3 of oxygen on the left and on the right, and the common multiple is 6. And so she just figured it out like that way. Is that something that is pretty universal that we could apply to like problems like that?
I don't know. That seems like a good guess, like a lucky guess. You saw a 3 and you saw a 2, and so you tried to aim to get to 6. Except that we never took advantage of that subscript 3. We never multiplied it by anything. Yeah? So what I would say is, together I can get 4, but that 4 never worked out because then my carbons were unbalanced. So then I'll just go to the next even number. Can I get 6 oxygens to balance? If that wasn't going to work out, can I get 8 oxygens to balance? Ultimately, the carbon there was kind of a wrench in the whole problem. All right, part A was asking, if we have 10 grams of iron 3 oxide, how many grams of iron metal can be generated? 10 grams of iron 3 oxide. This is what I know right now. Grams of iron 3 oxide. What's the only thing I can do with this? Molar mass into moles of iron 3 oxide. From there, what did you guys do? Mole to mole ratio, iron 3 oxide on the bottom. What did you put on the top for A? A is asking how many moles of iron can be made. So you put moles of
2 moles of iron.
and we're not even asking about numbers just yet. If we set up our units, the numbers will all fall into place. The last one, I've just crossed over the mole to mole. Now I want to figure out mass of iron. So once again, I need the molar mass, this time of just iron. All my units canceled. Grams of iron 3 oxide, moles of iron 3 oxide, moles of iron. All right, help me fill in some of these numbers. What'd you put in here? Cole? 459? 169 point.
It's 159.68.
159.68. That's okay. What'd you put here? 2 over 1 from the balanced chemical equation. And what'd you put here?
55.845 over 1 mole.
Good. Once you have the units in place, the numbers just fall in line. If you try adding in the numbers, it can clutter things a little bit more. That's why I like to do the numbers last. All right, you plugged all this in. What'd you get? Well, actually, let's ask this first. Do we think that the 10 grams of iron 3 oxide will result in a mass that is heavier than 10 grams of iron or a mass that is less than 10 grams of iron? I should make twice as many moles of iron, but also iron weighs way less than iron 3 oxide. So what'd you get?
6.99.
Grams of iron. Good. The second is how many grams of carbon dioxide is generated. I can actually repeat a lot of this information. I'm still converting from grams of iron 3 oxide, but now in my mole to mole conversion, I'm taking 1 mole of iron 3 oxide to 3 moles of carbon dioxide. And then I need to convert 1 mole of carbon dioxide, we talked about this earlier, weighs 44 grams. So grams of iron 3 oxide, this first conversion is exactly the same. Now I'm just converting into a different chemical. What'd you calculate here?
8.268.
83?
Yeah, 8.3. Well, sorry, 8.3.
8.3 grams. Great. Once again, we're following the same route on our roadmap. We're going from mass to moles to moles to mass. All right, and then the last question was, what chemical species here is being reduced? Dalet, you want to answer that one? In this chemical equation, what is being reduced? Iron is being reduced from iron 3+ to elemental iron. Well, that's a little bit confusing. Iron 3+ is reduced. Great work. The challenge on that one was the coefficients predominantly. All right, problem number 2. Potassium chlorate decomposes to form potassium chloride and oxygen gas. If roughly 2 grams of oxygen gas is wanted, how much potassium chlorate in grams is needed? Do you guys want to give me your chemical equation?
We did 2 moles of potassium chlorate, which is KClO3, leads to 2 moles of KCl plus 3 moles of O2.
How challenging was balancing this chemical equation? Not as hard? Good. We can see that potassium balances, chlorine balances, 6 oxygens on the left, 6 oxygens on the right. This tip for doing these types of conversions is find information that has 1 unit and start doing your conversions from there. This question said 2 kilograms of oxygen gas is wanted. Mass of something. How much potassium chlorate in grams is needed? I need to know moles of oxygen, then I can do moles of chlorate before I can figure out the mass of that chlorate. So this is pretty much the same as the one we just did, but we're kind of looking at it backwards. Here, I had a certain amount of my starting material. I wanted to know how much of the products I could make. Now, I have a certain amount of product that I want. I need to figure out how much of my starting material I need. 2 kilograms of O2. Can I convert into molar mass directly? What was your first conversion? Kilograms of O2 to grams of O2. And then from grams of O2, moles of O2. From moles of O2, mole ratio. Moles of O2 to moles of KClO3. Then where'd you go? Good, moles to mass. We're just following that roadmap. Each of these is a conversion factor along the way. What numbers did you plug in for the first conversion factor? You put 1,000 on the top? 1,000 grams in 1 kilogram. Small unit, big number. Big unit, small number. What did you plug in for your second conversion factor? How'd you get 32? When I look at the chemical, the periodic table, oxygen has a molar mass of 16. Good. O2, 2 times 16. What's your mole ratio of potassium chlorate to O2? Good. Coefficient 2 for chlorate, coefficient 3 for O2. And your last conversion factor, molar mass of potassium chlorate? 122.55. Let's check that the units cancel. Kilograms of O2, grams of O2, moles of O2, moles of potassium chlorate. By the way, this is what airplanes use to produce oxygen. So that's why we're saying I want to make sure I can produce 2 kilograms of oxygen so that a passenger has enough oxygen to breathe while the plane plummets. So how much potassium chlorate will I need to decompose to get that much oxygen? All right, what'd you get? So this might have been better to put as kilograms. Approximately 5.1 kilograms of potassium chlorate. Great work. All right, problem number 3. A titration problem, which tells us that we're looking at what type of reaction? Acid-base reaction. The decomposition, is that redox, acid-base, or precipitation? It's redox. Oxygen is bonded to chlorine, and then oxygen is bonded to itself, which means oxygen is losing electrons. Oxygen is being oxidized. Chlorine is taking electrons back from oxygen to become chloride. So chlorine is being reduced. Chlorine is gaining electrons. Oxygen is losing electrons. Titration in problem number 3 tells us we're doing acid-base reaction. What was your chemical equation?
3 calcium hydroxide plus 2 phosphoric acid reacts to make 6 water and just 1 of the calcium phosphate.
All right. Calcium hydroxide, CaOH2, phosphoric acid, H3PO4, calcium phosphate, Ca3PO42. Already balanced. How was it on balancing? A little tricky. Phosphate should be fairly easy to balance. The calcium should be fairly easy to balance. And if you can balance those two, you typically balance the water, the hydroxide, and the hydronium. Now here it's a tricky part. 20 mils of a 0.2 molar calcium hydroxide solution requires how many mils of a 1 molar phosphoric acid solution? So I want you guys to, if you still have this sheet that I gave you last time, I want you to make this correction, which is to say that you can convert from moles to liters using molarity. You can convert from moles to volume using molarity. These two things should be flipped. Molarity has how many units? 2 or 1, depending on how you look at it. Molar is the unit of molarity, but we can write that as moles per liter. Moles per liter is a conversion factor. So, what piece of information are you given in 3 that has just 1 unit? 20 mils. And that's where we should start. 20 mils of the calcium hydroxide. What conversion factor can I put in that has milliliters? Well, nothing. So I'll convert from milliliters to liters. And then I can cancel liters of calcium hydroxide with moles of calcium hydroxide. What has moles per liter as a conversion factor? Concentration, molarity. Now that I have moles of calcium hydroxide, I can do a mole to mole ratio. Moles of calcium hydroxide on bottom, moles of phosphoric acid on top. Do I want to end with moles of phosphoric acid? So I need to cancel moles of phosphoric acid. What conversion factor will give me moles of phosphoric acid and some other unit? Its molarity. Its molarity is given to us. So I can put liters of phosphoric acid on top. And then again, it wants milliliters, so we'll have to convert liters into milliliters at the end. If you are a smart person, you'll recognize that I'm doing a conversion from milliliters to liters and then from liters to milliliters. So I can actually just ignore those in my calculations. They're going to cancel each other out. Let's just fill it in for now. 1 liter is 1,000 mils. Concentration of calcium hydroxide was 0.2 moles per 1 liter. What did you put in the mole to mole ratio? 2 on top, 3 on bottom. Coefficient for phosphoric acid, coefficient for calcium hydroxide. What did you put in here in your last conversion factor?
That would be the 1 over 1.
1 over 1.
1 over 1.
Oh, it is, yeah.
Yeah.
1 liter with 1 mole in it. That's 1 molar. And then, of course, 1,000 mils in 1 liter. So the numbers here are actually pretty nice despite it being very long. 20 times 0.2 times 2 divided by 3. What did you guys get for the volume of phosphoric acid needed?
2.67 milliliters.
2.67 milliliters of phosphoric acid. Think about this. Phosphoric acid, 5 times as concentrated as calcium hydroxide. So I'll need a much smaller volume of phosphoric acid to neutralize the larger volume of calcium hydroxide. We have run out of time. We'll pick up with 4 on Monday, and we'll go from there into our gases unit, Unit 8. Have a good night, guys. A good week. Good weekend.